Okay, hi class, this is another video boost. It's November the 18th, 2010. Okay, what I want to do is extend you a little bit and start working with H3O+, as we're going to be in class this week. We're still doing addition reactions. If you're adding H3O+ instead of HCl, you should see this as being similar to HCl, okay, or HBr. So what you would do is you would take the pi bond, hit the H, and knock out the water. It doesn't matter which bond you use. We're just saying one of them is a pi bond, okay? When you do this, you would obtain this carbocation, okay? And using what you learned in class this week, we learned how to classify carbocations. So you'd want to ask yourself, what kind of carbocation is this? You would say it's a secondary carbocation. And then what you learned in class this week is to look at the adjacent carbons and look at the order of those carbons, okay? And if one of the adjacent or both are higher order, you would predict a rearrangement. Now in this case, this carbon is secondary and this carbon is quaternary. And I know you know how to classify carbons. So on this side, you would not predict a rearrangement. On this side, you would predict a rearrangement. So what kind of rearrangement would you predict? You would predict an alkyl shift. Okay, now, in this case, there's one alkyl shift that's really simple and really obvious. And that's the shift of this methyl group over. And that's very much like what I did in class. But what's going to be tough for you is getting used to the idea that a carbon, these carbons here, are really no different from that carbon there. And this is always a very tough problem for students. It's sort of like when I told you that, and we debated this for days and days and days, I told you that 1,3-dioxyl interactions were the same as gauche-butane interactions, and people really struggled with that because people do not like rings in general. Rings are tough. But the thing is, this carbon, and this carbon, this bond, and this bond are all the same distance from that charge. And you have to kind of build your models, think about it a little bit. So the truth is there's two alkyl shifts I could do here. I could shift the methyl over, or I can actually shift the ring over, or this ring carbon over. So let me show you how you would do that. Okay, I'm going to get rid of this HCl. Okay, alkyl shift, you would take this carbon and shift it over here. Remember, what you're moving is a CH3 minus. So what you would obtain is this. And you would get a plus charge there. Remember, the purpose of the shift is to obtain a more stable carbocation. Okay, but the other shift would involve one of these two, and they're exactly the same. So I'm going to show it from the bottom. I could take this bond and move it over there. So what I'm doing is, it's like I'm making a bond here, and I'm breaking that bond right there. So I'm going to draw it in a similar shape. And I want you to practice this. Remember I told you that the first problem on the flashcards is ridiculously hard. The first problem on the flashcards is like this problem. So this will prepare you for it a little bit. Okay? So what I did was there was a bond here, and I shifted it over there. Okay? And that is no different than shifting that methyl over. So where does the charge end up? The charge ends up where you took the bond away from. Okay? Now, what were you taught to do in class? You were taught in class to just start attacking all the cations that you made. But in this case, you would not be attacking with a halide. You would be attacking with water. Okay, so I want to show you what you do with water. Okay? You would take the water and attack each of these cations in turn. Why am I attacking all of them? Because, as we said in class, carbocation rearrangements take time, and you actually don't have a sense right now of how long it takes for a carbocation to rearrange. So the truth is, it's highly likely you would get attacks on all three of these. Okay, so what would they look like? I don't want to totally lose track of what I was doing here. What's the time right now?
4 minutes, 58 seconds.
Perfect. Okay, so I don't want to lose track of these. So what I'm going to do is draw all the routes. Now look at this ring here. This is really 1, 2, 3, 4, 5, 6 membered ring. And it might help you to number it. If you numbered it, it'll help you keep track of things. So this is really a 6-membered ring. So I'm going to kind of take the kinks out of it and draw it like this. And then on number 1, there's a methyl. And on number 2, there's an ethyl. And where is that charge? That charge is on number 1. Okay, so that's what I've got. So the water attacked this here, so it would look like this. That's one initial product. Now notice when it first attacks, it has a positive charge. What's different about this is you're attacking with a neutral atom. Okay? Next one. You would get that, okay? And then finally, you would get this, okay? Now the question is, what do you do with water? The way you want to think about the water is that this is sitting in water and that the hydrogens are going to bounce from one water atom to another, okay? So if you just had H3O plus sitting in water, the proton would not just sit on one water. It would constantly be exchanged between different water atoms. So what would happen here is another water would grab this H and pull it off. Now that doesn't mean the proton can't go back on there. It's just going to bounce off from water to water to water. And because the solvent is water and there's an infinite amount of the solvent, the proton essentially gets lost in the solvent. And I'm going to talk about this a lot in class. Now, if you were in lab, you would take some base out, and you would shake up your reaction with base, and that base would neutralize that extra proton. You would get rid of it. But the way we write it on paper is as though it's just kind of gotten lost into the solvent. Now, this would happen to all of these, so that ultimately, in each case, what you would have is an alcohol. This is actually a way to make alcohols. So what you would get here, I'll just rewrite this one. You can use some shorthand in your work. You don't have to keep rewriting the mechanism over and over and over again. So the thing is, in each case, the water would take the H off, okay, or you'd lose the H into the solvent. It would get statistically sort of diluted out, all right? So you've got this product, and this product. These two come from rearrangements. This is the original cation. And remember, I told you always to write the product from the original cation. Now, what you have to think about are any asymmetric carbons that you made in the process. So, did I make asymmetric carbons? Well, in this case, I actually made 2 asymmetric carbons. I made this one and that one. So, I'm giving it some dimension. So, this is now 3-dimensional. So, what else would I get? I get this plus its mirror image, right? And I would get, so when you're looking at some of these problems on the flashcards, you're going to see all these different variations. And then I get this plus its mirror image. What is the relationship between these two? You should know these are diastereomers. All right, these are enantiomers. Okay, so because you made 2 asymmetric carbons, you're going to get 4 products. That's the problem with carbocations, as I told you in class. You get attacks on both faces. Now this one, I only made 1 asymmetric carbon right there.
1 minute.
Okay, so you get this plus its mirror image, and then finally, in this case, you made 2 asymmetric carbons, so you would get, I'm going to put plus 3 stereoisomers. I want you to figure that out. Okay, so we'll discuss more of this in class. Okay.